Hi everyone, this is the second session of Applied Statistics in Healthcare, the multiple linear regression course. And in week 2, we are going to look at methodological issues, variable selection, the assessment of the model fit, missing data, interactions, and non-linearity. These are things that can be issues or things that we want to improve on to give ourselves better results in our multiple linear regression. Okay, so we'll start with the methodological issues. Issues that can make the regression results less reliable and their solutions. To read more, see the Herald book, chapter 4. So let's go over a review of regression. On the top half, this is what it looks like when we have no regression applied to our data. A common approach to predicting outcomes is to use the average outcome. For example, with the average length of stay, we might assign 3 days for everyone. If the overall average is 3 days, then we might just predict each patient's average length of stay to be the 3-day average for the entire sample. So what that might look like with data, we have in the miles per gallon on the y-axis, and we have it graphed by the rear axle ratio values for each car. And so what we do have with our gold lines, we have the average for the outcome for the miles per gallon and the outcome for the predictor rear axle ratio. And we see a blue dashed line that overlays that average for the miles per gallon for our outcome. And that blue dashed line is our trend line based on a mean. So this could be our default model. It's not a regression model, but it is when we assign that default value of the average, which is about 20 miles per gallon for every car. So we're just displaying on the x-axis the different rear axle ratios for all of our different cars. And we're just matching up those points with the miles per gallon. And so what that might look like if we assign that value, we're going to have some predictions that are high or low, and maybe for a very few of them they're going to be the exact 20 miles per gallon. That's the average. So we have 2 cars listed here. On the bottom left we have the Mercury 450. On the top right we have the Fiat X1. And where their names are at, that's where that value's at. There's a little dot right below the Fiat and a little dot right above the Mercury. And those are the actual miles per gallon for those 2 cars. And so if we use our overall mean, which happens quite often, if we use that, we can see that the distance between each car and that expected line, the trend line that blue dashed line, that distance between the actual value for these 2 cars, we see that red line representing the distance or the residual between each car's actual value and the overall mean that we're assigning to all cars. And we can see that distance can be higher or lower than the value that we're assigning. So even just by looking at these couple pieces of data, we can see there could be a big part of residuals or error in assigning the overall mean to all our different cars. And on the bottom half, this is what regression adds. A regression calculates a trend based on a predictor variable, in this case the rear axle ratio. We see as the rear axle ratio increases, so does miles per gallon. So we see on the lower end, cars with the lower rear axle ratio, such as the Mercury 450, have a lower mile per gallon value than something like the Fiat X1, which has a higher rear axle ratio and also a higher miles per gallon. So we see that same distance between the actual value for the two cars, their actual MPG, and then we see a portion of the red line in the above graph. We see that a portion in green, and that would be the distance between the average miles per gallon and the predicted line, that blue dashed line. And in this graph, that blue dashed line that's at a diagonal represents the predicted values, and this is what we get from a regression. So we can see that if we follow the predicted values for that blue dashed line, it gets us closer for both values, and what we see in green is what the regression line offers us in terms of a better prediction. We see that what was a bigger residual on the above graphs, say for example on the Fiat, that's a bigger error in that approach of just assigning the overall average to all cars. We see in green on the bottom half, we see that's the portion of our prediction that has gotten closer because we're using that regression line, which we see as that blue dashed line. So we see the red on the bottom half smaller compared to what's on the top half. That means our error has gotten smaller when using this regression line. And that blue dashed line follows the pattern that we see in the actual data, which are those little hollow circles throughout the graph. We see just by looking at those hollow circles, we can see that there's a pattern there where higher rear axle ratios tend to give us higher miles per gallon. And so from that pattern, we develop a trend through our regression, and we see that in that blue dashed line. And by following that pattern, we get a predicted score where that blue dashed line falls underneath the Fiat X1 score, as well as the Mercury 450 score. So that would mean that by using a regression line, our guesses are smaller. The errors in our guesses are now smaller than they were by the traditional approach of just assigning that to everybody. And so we see in the sum of squares of regression, that's 522. The sum of squares of residuals is 604. So the regression on the top, if you were to add up all those green parts that you see in the bottom half, in the bottom graph, that would come out to 522 if we sum it for all cars. The residuals, the red, if you were to sum that all up, that comes out to 604, and then you have an R-square formula of the regression divided by the sum of the regression and the residual, and that's 0.46, and that's how we calculate our R-square. So we see about half of the information that we have, half of the variation that we have, almost half is explained by our regression line. And the red lines from a regression are much smaller now. The green lines are the contribution from the regression, and 0.46 is a large R-square effect. So that's a pretty effective model. So from that, we can also begin to look at things that can even give us a better estimate, and these are methodological issues that we need to take into account to give us better results. Just by using a simple regression just on that rear axle ratio on miles per gallon, we were able to get a better model, or a better predicted values based on that trend line. So now we can improve it in other ways, and we can do that by handling common issues and applying the right statistical solutions. And one common issue are small samples. Issues with smaller samples, samples less than 500 to 1,000 cases, it varies by the type of study. Issues are that we have less precision in results, which presents itself as coefficients closer to zero, meaning a smaller effect, and larger standard errors. And standard errors are that the denominator part of our t-statistic, which we use to determine significance. And that's to determine if we're actually seeing something and we're correct in saying that we see something that's there and when it actually is there. This in turn gives us bigger confidence intervals and smaller test statistics. So in other words, we get less significance. Smaller samples tend to underestimate significance. On the contrary, large sample size, those greater than 5 to 10,000 cases, depending on the study, can make minor effects look very significant. Various statistical methods can help get more accurate results with small samples. Power analysis can help identify small, medium, and large effects. Effect sizes are independent of sample sizes. So we can say, is this a significant effect? That can really depend on the sample size. If it's too small, we might miss something important. If the sample size is too big, then many things can look important when they're really not. So what we really want to know is it statistically significant? And if so, is it a statistically substantial? Is it a big enough effect? Are we seeing something really important? On the second slide, collinearity and data reduction. Collinearity, which we discussed last time, begins to happen when predictors are highly correlated. For example, a correlation above 0.80. And that gives us greater negative impact when there is a higher correlation. Collinearity can increase standard errors and produce coefficients that don't make sense. Our results don't really help us understand what we're looking at. The solution to multicollinearity is data reduction, such as hierarchical cluster analysis, principal components analysis, or latent variables. Just like with smaller samples, we can use different approaches to give us more accurate results. So a solution of having smaller sample sizes would be to use methods that give you the most accurate results. Composite variables can be made as the average between two highly correlated predictors. For example, if we have a correlation value R that's greater than or equal to 0.90 to 0.95, such as the mean blood pressure, that would be the combination of the systolic blood pressure plus diastolic blood pressure divided by 2. That's a composite score. Another issue is confounding, and that's a lack of initial comparability in baseline factors or variables that leads to biased estimates of outcomes. For example, the treatment group was picked from younger patients while the control group from older cases. Age is a confounder. So if one group naturally has is just by default different in another variable, such as age, if one group's a lot older than the other group, we might see positive test results. It may look like the intervention group is doing a lot better than the control group, but that could be because the intervention group's a lot younger. And if health outcomes are related to age, then we have confounding. And so when treatments are compared, groups are often quite different because of lack of randomization, and that's normal. We're doing observational studies. We may be seeing the patients that come in versus those who don't. So it could just be a natural part of the data or the sample that we're examining. Subjects with specific characteristics are more likely to have higher or lower values on other predictors. The figures below shows confounding and adjustment. And on the right side, we can say that we adjust that could be the solution, that we add these variables into our model so that we balance them. Because we can't balance them before they came into the hospital, we can balance them mathematically. We can balance those effects through regression. And Moron confounding, we can calculate confounding by comparing coefficients in two models. We call a model with one predictor the crude model, and we call a model with two or more predictors the adjusted model. That means we're looking at one effect, such as age, adjusted by gender. If the effects in p-values changes at a substantial amount because of adding the second variable, we have evidence for confounding. For example, the crude model for the gender coefficient drops to 0.066 after adding age into the adjusted model. So if we look at the table on the bottom right, we see three models: the crude, the adjusted, and the interaction model. The crude model on top has gender. That coefficient is 0.381. And when we add in, and this is the model for gender, and when we add in age to that model, that coefficient goes from 0.381 to negative 0.066. So that's a big change, to go from having a positive effect that was significant to having a negative or an equivalent to zero effect by adding in age. So we know age is a confounder if it has that big of an effect. The crude estimate is 682% larger than the adjusted estimate. We have a formula of how that was calculated on the top right, and that greatly exceeds the 20% rule for important confounding. So if it had been 20% larger, then if the crude estimate was 20% larger than the adjusted estimate, we'd already consider that an important source of confounding, but this is 682%, so that's a really big deal. So we need to definitely include age into our model. We can also determine that age modifies the gender effect from the significant interaction coefficient of negative 0.030. So on the bottom, we're multiplying the effects of age by gender. So if it's a female effect, we would multiply age by a value of 1 for when patients are women, and if it's when the patients are men, then that age times 0 would, all numbers multiplied by 0 equals 0. So for the interaction, it would give us the effect of when women's age on the outcome. And we can also determine that age modifies the gender effect, and we see that with our significant effect on the right side. The second column from the right, we see that the probability is 0.015, so that's a lot lower than the 0.05 cutoff we might use. We should use the interaction model's results. So that was when we looked at assumptions last time. There was the assumption of additivity. This would actually give us evidence that we should relax that assumption of additivity, instead using an interaction to represent what we have in the data. And then another common issue is overfitting, and that's having too many predictors or too many degrees of freedom which can cause overfitting. A model may not be as reliable in future samples. So we might get a really great model if I begin to use too many variables on, say, the CARS data set, which has just 32 rows of data. If I start using maybe 4 more predictors, then I'm starting to increase the chance of overfitting. This model might look great on the data I'm using right now, but in the future it might produce poor predicted values for our outcome. Adjusted R-square, and it's adjusted for overfitting. Calibration and discrimination statistics can can provide more accurate results on model quality, especially for discrimination. That'll give us an idea if we do model validation. That can tell us what we're likely to see in future data. A rule of thumb is not to use more than 20 predictors in a model. For example, if we set an alpha level of significance to p is less than 0.05, if that's our cutoff, and we have 20 significant predictors, then there's roughly as high as a 100% chance that we are wrong on at least one predictor being significant. So in a regression, we have our overall model results. That tells us how good the collection of variables are working. And then we have for each predictor that we use, for example, if we had age and gender and health status, we have 3 predictors, and we're in effect doing 3 hypothesis tests. So that probability of that p less than 0.05, that tells us what's the probability of saying that there is a significant effect when there really isn't one, which we call a type 1 error. That value, that p is less than 0.05, that is meant to describe the probability for each predictor. So if we have 20 predictors and we have 20, in effect, we have 20 hypothesis tests, and if we get the overall probability, if we sum up all those probabilities, then there's a chance that there could be one predictor there that may look significant, but just by chance. And so that's 20 times 0.05. That gives us that 100% chance that we could be wrong on at least one predictor being significant. So we need to consider each predictor's result as a hypothesis test and a type 1 error. And we have things called Bonferini Bounds, and those help give us accurate alpha levels on being wrong. So when you do a Bonferini bound, it won't actually be 100%. It won't be 20 times 0.05. It'll give you something that would be a lower value, but in general, we probably wouldn't think that there would be 20 different causes for the outcomes results. Say, for example, if we're looking at lung cancer, we may not consider there being 20 different reasons why a patient might have lung cancer. We'd probably want to adjust for many things, but less than 20 is a pretty safe number of predictors that should give you reliable estimates in future data. And so that brings us to variable selection, and that's selecting an adequate number of variables that prevents overfitting and omitted variable bias. I have Harrell's Chapter 5 and Rosner's Chapter 11 as other things that you can read if you wanted to learn more. So I photocopied a couple parts out of Frank Harrell's book, and so he suggests what we call the limiting sample size. If you divide that by 10 or as much as 20, that can tell you about how many predictors you could have. And then on table 4.1, we see his chart his table for what he would consider a limiting sample size. When the outcome is continuous, such as what we use in multiple linear regression, then the limiting sample size would be the n, the total sample size. So for that car data that we're using, it has 32 rows of data, so that n equals 32. So his limiting sample size of m equals n, the sample size for multiple linear regression. So if we divide, since m equals n, if we divide n by 10 and n by 20, that suggests that we can use 1 to 3 predictors in our model. Harrell prefers using n divided by 15, which is 2 predictors. So about 2 predictors, 2 to 3, is about as much as we'd want to use in a regression model. And so that's one way that we can determine the number of predictors that we can use. So at max, we might want to use up to 20 just to give us a model that should do well in future data. But it also depends on our sample size. When we have about 32 rows of data, like the cars data, then we'd probably want to use about 2 or 3 predictors. And another thing with variable selection, we'd want to keep the most important predictors. A model with all clinically relevant predictors is better. But if a parsimonious model is desired that has the most power with the least number of predictors, we can determine the variable importance to give us an idea of what things we should keep. We can rank predictors by standardized regression coefficients. Not all predictors are on the same scale. For example, car weight and horsepower. A value of 1 means 2 different things for those 2 variables. So this helps to show which predictors have the biggest impact on the outcome. Rosner has an example on page 471, and again, these are standardized regression coefficients. But Harrell's variable importance is a better option. It uses the F statistic from the ANOVA table. The larger the value, the more important. And we have an example below. For a 3-level category, such as a high, medium, and low rating, the F statistic is multiplied by 2. And we get that number 2 by getting the number of levels, which is high, medium, low. Those 3 levels minus 1 gives us a value of 2. So if the F statistic has a value of 10 for that 3-level category, we would then multiply 10 times 2, the 3 levels minus 1. So that value, that F statistic of 10 multiplied by 2 would give us a value for importance of 20. And so we can see on this graph on the right, this is a variable importance graph. The bottom variable, WT, which is car weight, has a value of 12.7. And so if we go over to the ANOVA table, we see that under the F statistic, we have in that WT row, we see it's 12.71. So that's your most important predictor. I think this is maybe the most useful way to define variable importance. Another very useful approach is called the KK information criterion, or the AIC. With that, you'd want the best performing model uses the one with the lower AIC. So you can see what models look like before and after adding in predictors, and something that gives you a sizable change would suggest it's more important of a predictor. And now we can do the assessment of model fit, examining model performance and effects of each predictor. So again, we have the overall model performance, which means how all the variables work together, and we usually determine that through R-square. And we also can assess model fit based on the impact of each predictor. So if we have 3 predictors in that model, we would look at how each of those 3 predictors perform as well. And you can see these different authors to read more. And here's a common set of model results. The R-square and coefficient results are more commonly reported results. And the software I use, I get this big output, but on the top right of this output, we see the R-square and the R-square adjusted ADJ. That's common in probably every software, every statistical software. And the coefficients on the bottom, those are common to this regression table. To the left, we see coefficients. That's HP, WT, and AM. AM is an automatic or manual transmission. A value of 1 here is for the manual transmission. These are called parameter estimates and regression weights. They're the same thing. We can multiply cars' variable values by the coefficient to calculate a predicted miles per gallon. So you can use, we have the intercept on top, and that's standard in all models. But you can use these 4 different values to multiply the values that you have in your car, or for each row of data, and you can use this to calculate predicted miles per gallon. So on the top right, we again see the R-square, and that tells us the proportion of variance in the outcome that is explained by the regression. This tells us how good the model works. 0.84 is very high. You can use that to actually predict individual expected MPGs for cars. And right below that, we have something called the adjusted R-square, and this gives us a more conservative estimate to adjust for overfitting. So I have 3 variables here. That might be considered too many variables. 2 or 3 is about how many you would expect to use. But if we use 3, then probably a better estimate of R-square would be 0.823. That's probably what we're going to see in future data if we apply this model with future data. And this is how we can interpret model parameters. When we do a regression and when we look at each individual predictor, what we are doing is that we are testing if the coefficient b, which is the values, b represents the coefficient values that you see, negative 0.03, negative 2.87, 2.08. Those are the beta coefficients for each predictor. So we are testing if the coefficient b equals 0. And that's our hypothesis. Our null hypothesis is that our beta coefficients equal 0. So again, on the top, from our R-square, we can see that the model fits the data well. It has a large effect. Our R-square is definitely bigger than 0.26, the cutoff that we saw last week. And we can say it's very predictive. Its R-square is greater than 0.70. And how we would interpret this is that, let's start with the intercept on the left side. The MPG of 34 is when all predictors equal 0. So we see the intercept, the value next to it is 34. So when horsepower, weight, and we have an automatic transmission, when that's the case, we'd expect our miles per gallon to be 34. For horsepower, HP, that value of negative 0.03 would say that for every 1 unit increase in horsepower, there is a decrease in miles per gallon by 0.0375, controlling for all other predictors. So again, by including weight and automatic and manual transmissions, we're now controlling for those 2 predictors. So that's why we say that last part, controlling for all other predictors. In other words, we're making all things equal on weight and automatic or manual transmissions. And how we'd interpret WT, which is weight, for every 1 unit increase, there is a decrease in MPG by 2.8786, controlling for all other predictors. And when we look at the coefficient for weight, that value is negative 2.8786. And for automatic or manual transmissions, for a manual transmission, there is an increase in miles per gallon by 2.8. Oh, that is a mistake. It should be 2.0837. I have a typo there, controlling for other predictors. So that positive value of 2.08 indicates that as we go from an automatic to manual transmission, we tend to see higher miles per gallon. And then we have the other value that we often look at would be on the far right in this regression table, and that would be the p-value. And so we have values that range from less than 0.0001 all the way up to 0.1413. So how we can interpret that would be for For the intercept, it's always going to be significant. It's just a standard value that we get with every regression. But our three key variables of interest would be for horsepower, this is very significant, that 0.0005. The confidence interval on coefficients does not contain 0 as a possibility. So again, we're testing to see if the coefficient is equal to 0. We're using a confidence interval, which I'll show you a graph next. But within that range, that normal range, we don't expect to see 0 as one of those values. So in that case, in other words, we would fail to accept our null hypothesis that beta equals 0. We don't expect that there to be no effect between high or low horsepower cars. For weight, we see something significant, WT. The p-value on that is 0.0036. This is also significant. The trend is not, another way to say it is the trend is not flat. We feel confident that weight decreases miles per gallon. So the heavier the car, the lower miles per gallon we expect to see. And for AM, the automatic or manual transmission, the trend is not significant. That value of 0.1413 is a lot bigger than our cutoff of 0.05. So a difference of 0 can happen in between automatic and manual transmissions. In some cases, you'd expect them to have a very similar, a statistically similar miles per gallon rating. And so we just mentioned confidence intervals. So I'll give you more information on, so we'll cover more on using confidence intervals to test regression coefficients that beta equals 0. So this shows the summary of the different effects. For horsepower, and they're going, for horsepower and weight, it's going from the first and third quartile. Sometimes a value of 1, which we get in those, in the last slide's coefficients, our results. The difference of going from of a 1 unit increase, but sometimes it's more helpful to see a jump from the low end to the high end, and that could be the first to the third quartile. So we're going to look at that for horsepower and weight, but we still get the same idea. For horsepower, if a 95% confidence interval contains 0, then it is possible that no effect may be associated with the predictor. And that value of 0 is right here, and it's circled. There's a red circle around the value of 0, so we want to make sure that for things that we consider significant, we want to make sure that our confidence intervals don't touch this dashed vertical line at 0. For example, horsepower and weight are significant predictors of miles per gallon. We clearly see 0 does not lie within the blue bars for each coefficient for those for horsepower and weight. They're actually kind of far off from 0. However, 0 is within the blue bar for transmission. We see that that dashed vertical line does fall within the blue bar, so it's possible that if we had many random samples, that a difference of 0 would be found within many. So if we had more data, more samples, then we could probably see in some cases where the miles per gallon for automatic and manual transmissions were pretty much identical. And here are our model results. Below we have an ANOVA table with F statistic results that indicate significance. The bottom two lines are the regression and residual error components. The ratio of 48.96 and a p-value of less than 0.0001 indicates a significant regression and at least one significant predictor. So if we only had the regression line and the error line, And actually, if we just had the regression line, we would say, yes, this is a significant model. And because it is significant, we know at least one of those predictors must be significant. Here we can see it's because we have the full set of rows of data, we can see that it's horsepower and weight. But these are the part of the analysis of variance table, and that ratio, that 48.96 is our F statistic for the model, and that gives us an idea that it is a significant model and at least one predictor is significant. So now we're going to go to missing data. We may not have this as much with hospital data, but we tend to see it sometimes with income and education and maybe other self-reported statistics. See Harrell's chapter 3 if you wanted to read more. We have different types of data. We have the first one would be missing completely at random. It's random in the strictest sense. Data loss maybe because test tubes for labs are broken. We have something called, which sounds similar, it's called missing at random. Data elements are not missing at random, but the probability that a value is missing depends on values of variables that were actually measured. For example, in a survey that asks about personal income, one group is less likely to answer, but the level of income is not correlated with the missingness. We can still impute income for them as long as we know they're in the group, and because the incomes we do have for some are a random sample of group's income. So as we go to each level, we're going to see that there's a certain pattern that contributes to missingness. So we can, for A, missing completely at random, that's just an accident that might happen, or some completely random explanation of why we have missing data. And as we go down these further levels, we might see that, especially for informative missing, that there's a pattern to why we have missing data, and it may be that missingness might be highly correlated with the reason, with the actual outcome. So we're going to have somewhat biased results in some situations because of missing data. We might just be looking at a certain set of data, a subsample. So we have to consider if we want to use these variables. For informative missing, for C, the elements are more likely to be missing if their true values of the variable in question are systematically higher or lower. An example is when subjects with lower income levels or very high income levels are less likely to provide their personal income in an interview. Missing completely random and missing at random are also called ignorable non-responses, while informative missing is called a non-ignorable non-response. So this is a type of missing data that we have to really look out for. And how to deal with missing data? First, we might, for proportions of missing data less than 0.05, this isn't a lot of missing data, so simple options are available. For example, for continuous data, you can impute the median value. For predictor and for a categorical variable, you can impute the mode. You can also choose to ignore missing data and go ahead and use the variables as is. So just going ahead and using this data and just ignoring that missing data is perfectly fine when you have when your missing data makes up less than or equal to 5% of the sample. And for proportion of missing from 0 to 0.05 to 0.15, if the predictor has no multiclinarity, you can do the same as the above. And if you do have some multiclinarity, then you're going to want to do something we call imputation, and that could be what we're going to call single or multiple imputation. We'll cover that in the actual case studies, but we're going to start to use our other data to try to predict those missing values. And once we predict the missing values, we're going to try to run a regression model from that. And when we have a proportion of missing data greater than 15%, we would use the same considerations as above, but now we're probably doing what we consider multiple imputation more often. And when we have multiple predictors frequently missing, we take into consideration everything above. But now we would greatly benefit more from using something along the lines of multiple imputation. And if the main interest is prediction, it is worth trying a single imputation to see if the resulting model predicts a response almost as well as one developed after using customized imputation. And if we have about 20% missing data, so for example age data, then it would require 20 imputations. So for every percentage that we have missing data, then we'd want to have one imputation. 10% missing for age, we'd want to do 10 imputations. And we'll go over that more when we get to our case studies. So interactions. This is when the effect of a variable is dependent on the levels of another variable. Classic interactions are age and gender. The gender effect might depend on age. Heart disease is one where things look differently between men and women in the younger years compared to their older years. And you can read more in Harrell's chapter 2. So when we have interactions, we can relax the additivity assumption. A model with no interaction term predicts similar trends between weight and miles per gallon for automatic and manual transmissions. They overlap. So in this, we're looking at two trend lines on miles per gallon. It's one for the automatic transmissions and manual transmissions. We're just looking at the two trends from an additive model. And this is the two trends when we create an interaction between the transmission and car weight. So from this we can see the effect of car weight on miles per gallon is dependent on the type of transmission. We relax the additivity assumption and allow for an interaction. The interaction is significant. It's less than 0.05, and the p-value is less than 0.05, and it significantly improves the model performance. So not only are we identifying something that happens in the data, it gives us a better model performance because we're adding more information into that model. Lighter weight cars, and how we can interpret this graph is that lighter weight cars with manual transmissions begin with a higher miles per gallon, but automatic transmissions generally have better MPGs over 3,500 pounds. So kind of those cars that you see over 3,500 pounds are usually more of the luxury models, and so they might have things added to how the cars were built that gives you that lower miles per gallon. And now we're into this last section of nonlinearity, and this is in our model assumptions, our multiple linear regression assumptions. We have the assumption of linearity, and that's something that we can relax. It's very seldom that you do see a perfectly linear trend. So instead, when we don't have that, we can allow our expected values to follow a nonlinear pattern for our predictor. Nonlinear trajectories, finding a trend that matches your data, potential transformations. To read more, see Harrell's book on chapter 2. And so relationships among variables are seldom linear. When we have a nonlinear relationship, we have three options. We can first use a predictor as is in the model. In other words, ignore the nonlinearity. Number two, we can use a nonlinear term in addition to the main effect. For example, we might have our model might be y equals x plus x squared. So it could be length of stay equals age plus age squared. We can use that in the regression model, or number 3, we can replace the predictor with transform values in the model. So we can try to transform the age, for example, to account for that nonlinearity and create a new value for it. All options can have benefits in different situations. Polynomials, that's the squared term or the cubed term, are good options in a variety of nonlinear patterns, and you can read more about this from Singer and Willett. But making changes can improve model performance and give more accurate results. Polynomials can show that some effects increase at a decreasing rate. So it could increase, but that steepness in the curve can begin to come down. So that's what I mean by increasing at a decreasing rate. Initially, the coefficients x, the coefficient for x could be greater than 0, and for x squared, our polynomial term, it could be less than 0. And that indicates the curve initially starts off going upward, but eventually comes down. We can calculate that point of inflection where the effects were off, so we can figure out where that change in that trajectory will happen. And you can read more about that in the appendix to figure out how to do that calculation. And here are different types of trends. We see that on the top left, this is what a linear trend looks like. It's increasing at a constant rate. The main effect, say for example, age, is greater than 0, so that means the coefficient is pointing upwards. There is no modified x. We're not modifying that age value in any way, so that equals 0. It's just a straight linear term. Here's what it looks like when our values are increasing at an increasing rate. The main effect could be less than 0, and the squared term could be greater than 0. And actually it can also be greater than 0. It's just kind of where our intercept is at. But we see that polynomial term's increasing the value, and that squared term is bringing that trend upwards. And then another thing that we can do is we can say it's increasing at a decreasing rate. Our main effect for age would be greater than 0, and our modified value of x, in our output, it would look like it's less than 0. And so for these, the main effect, I'm talking about the model results, the regression results that you would get. You'd have 2 rows of data for age if that's what we're modifying, and the original value would be the main effect, and for some of these it'll be less than or greater than 0, and then we'd have that modified term would be that second row. So for this pattern, it's coming down and then kind of gradually coming back up, and so we'll say it's decreasing at an increasing rate. And here's a hypothetical of a trend that's decreasing at a decreasing rate. So it's really coming down pretty fast. And for this bottom right window, it's decreasing at an increasing rate. The main effect is less than 0, it's a negative value, and the increasing rate is a positive value, means it's bringing that trend upwards over time. So the higher the value of x gets, the more that we see that it's coming up because of that modified term, that second row, with the coefficients greater than 0. So here's an example for the relationship between miles per gallon and horsepower. The relationship shows a steep downward trend initially that lessens to a milder level at 125 horsepower. So we see it drop, and then about 125 horsepower begins to level off. In other words, the trend is nonlinear and decreasing at an increasing rate. For right-skewed predictors, it's important to remember that outliers exist in the highest values. Natural log or log 10 transformations may improve model fit by giving a nonlinear are giving a linear relationship with the outcome. So that's another option you have, is to transform, which I mentioned earlier, which is to do transformations, natural log or log 10 transformations out with really positive skewed data. Other transformation options include square roots, inverse squared, and other options listed earlier. So now we have values from our model. This is from a linear model. We're just looking at miles per gallon predicted by horsepower. It's a linear relationship between miles per gallon and horsepower. So we see up top on the right, or on the very top right, the actual values are those blue hollow circles, and the red pluses, those are our predicted values. So it's the predicted value for each actual value. So from the red plus signs, we can see what that trend looks like. We can see that kind of straight line going downward. And when we look at our two highest values in horsepower, we can see that we have residuals of 3.7, and that's the distance between that blue hollow circle and that red plus sign. The distance between that would be 3.7 miles per gallon. And when we look at our car with the most horsepower, which is over 300, we see that the residual or air component, the distance between that blue circle and that red plus, that's 7.8. There is a distance there, so be aware of the influence of outliers in your model. When we look at model performance, that R-square is 0.602. The adjusted R-square is 0.589, which is very similar. AIC, we talked about that earlier. Lower values are actually better. We can get a wide range of values. So with this data, we'll see 181 for this value. But if we had a much bigger data set, we'd probably see a much bigger AIC. But we'd have the same goal to bring that AIC level down, get it lower and lower. The model that gives you the lowest AIC of the models you're looking at for your specific set of data would be the better performing model. But again, R-square is 0.602. So in this next slide, we're going to add a nonlinear term. You see above in the top center, this is the table for the model results. We have HP, that's horsepower, and we have HP2, and that's the squared value of horsepower. We see that for the main effect for horsepower, it's negative 0.2133. So in other words, it's got a negative coefficient, and the modified term, the squared value of horsepower, that's positive. So just from these model results, we can say that it's decreasing at an increasing rate. So we'd expect kind of a steep drop initially, but as we go through, as we look at higher horsepower values, we should begin to see that trend comes back up. So let's look at that data in the graph. So again, the blue circles are the actual values, and those red pluses represent the predicted values for each actual observed value. So we can see in that trend, we can see the red pluses begin to plummet. But as we get close to about 125 or 150, we're starting to see it level off. We don't see that as steep of a trend. And in fact, by the time we get to that last value of 300, we're seeing it come back up. So this is that when we say it's decreasing at an increasing rate, this is what we're looking at. We're seeing it drop initially, then come back up. And we, in our quadratic model, and that's what it's called when you have that squared value, we have improved model performance from adding in nonlinear terms, a nonlinear term to the model. So we see that R-square went from, in this last graph, 0.602. We see it increase to 0.756. So that's a really, 16 points is a big jump. And we see the AIC below that go down to 167, and we have the adjusted r-square value close to what we see with the regular r-square. So this is a better fitting model, and you can see how close the predicted values. And this, if you can picture connecting all these red pluses together, then you'd get that trend line, that regression line. And you can see how this begins to fit the data better. And the red pluses of predicted values now represents a curved linear trend in the data. And then we can also have different types of nonlinearity. Nonlinear relationships between miles per gallon and quarter mile time. This trend is better described as a cubic model. The MPG rate begins to decrease around 17. So we saw it come up and then come back down around 17, but then again increases around the quarter mile time of 18. So it comes up, then drops, then comes back up again, and then even begins to drop a little bit around the 21 mile point. So we may say that this may even be a quartic model because the trend decreases after 20, but only for one data point. So a cubic model is probably more representative of the data. So in this data, we say we have two peaks are around 17 and 20, and at least one trough, and that's around the value of 18, 17 or 18. So what we can do then is add in a cubic model. And so what we would do is we'd have qsec plus qsec squared plus qsec to the third power. The cubic model gives predictions closer to the observed score, but it is important to consider overfitting and interpretability of the model by your audience. A quadratic or linear model may have less overfitting and higher adjusted r-square. So these are the r-square for the three different models. We have the linear model, that is 0.175. We have the quadratic model, which squares qsec, and then we have the cubic model, which is that cubed value of qsec. We see the r-square goes up to 0.205. That may be a better model, but since we have a small sample, we may not want to base future predictions on a cubic model. We'd probably do better with the quadratic model. And these are called splines. This is taken from the concept of a draftsman spline. See the Herald RMS reader to learn more. Again, not many things have a true linear relationship between the predictor and the outcome. Splines are a valuable method for dealing with nonlinearity. These are piecewise polynomials similar to using a squared value or quadratic model. They can go beyond squared or cubed segments. So with this, we allow bending points at the value for x at 1, 3, and 5. We're going to allow it to bend at these points. Because we're doing that, it would give us better model results. Splines, especially restricted cubic splines, have advantages over other approaches and provide more accurate results and better model performance. For example, they can take any shape. Otherwise, we would need to specify the shape by creating age plus age squared plus age cubed. So rather than trying to go through that, it would be easier to just apply your splines and let your splines get calculated and find those nonlinear trends in the data. I have this in my Shiny app if you want to try it out, but I think a lot of statistical software now use it. In summary, if a predictor is transformed, you only need to include that transformed value as the main effect. If making the predictor a nonlinear fit, you need to add both the main effect in its original predictor values and the transform values. For example, miles per gallon equals horsepower plus horsepower squared. Consider your audience. If you are interpreting effects for your audience, using nonlinear terms will be more helpful than complex transformations. But if you get an effective transformation and you're only interested in the predicted values, transform variables will be easier to use than the 3 degree of freedom cubic models. And so that's it. We'll start here next time. Thank you.